So in this video, we're going to talk about a different type of isomer for our alkanes. And that's going to be our conformational isomer. And also at the end of this video, since there's not a lot of exciting chemistry that we can do with alkanes, we'll tack on properties and reactions to keep our alkanes to 2 videos. With the conformational isomers, what we're talking about is, in alkanes anyways, the fact that with a carbon-carbon single bond, we're allowed to freely rotate around those single bonds. And the structure that has the lowest energy is going to be the one that puts whatever groups you got going on your alkane as far away from each other as possible. Remember that these bonding domains, these electrons that are involved in bonding, are electrons after all, right? And there's a coulombic force of repulsion associated with bringing like charges near each other. So bringing bonding domains near each other, or bringing groups in general, right? To nuclei near each other, to lone pairs of electrons near each other, any of those situations where you're bringing like charges near each other, there's going to be some undesirable energy or some repulsive energy going on. So when you have a molecule and it has the opportunity to sort of like make itself more comfortable, in other words, so rearrange its groups in such a way that puts them in a position where you can minimize that disruptive or undesirable energy, it will. And with alkanes, we have this free rotation around our carbon-carbon single bonds. So we'll start with our acyclic compounds. Just to see what this kind of looks like. You can take out your model kit if you have one and build these molecules as we're talking about it and spin around the carbon-carbon single bond and see, like, hey, I watched these hydrogens move around. In one conformation, they're sort of like one behind the other if you're staring down a carbon-carbon single bond, or if you turn it just 60 degrees, all of a sudden you can see, if you're staring down the carbon-carbon single bond, you can see all the hydrogens on the molecule. So in one instance, they are eclipsing each other. In another instance, you can actually see them all because they're staggered, right? So we're going to discuss something like that. And I'm just going to keep it sort of as simple as possible and begin with ethane. So I'm going to draw out the expanded structure for this. So we have 2 carbons. And each one is fully saturated. So this is just ethane, so CH3. CH3. We have different ways to look at this molecule. We'll draw the different ways out here. Again, if you have your model kit, might not be a bad idea to make this molecule. So different ways to look at ethane. So we have the expanded structure without proper geometry. Remember, these carbons are sp3 hybridized. So each one of those carbons has sort of like a tetrahedral electron geometry to it, right? The first way that we can look at this molecule is to, and this will be like an introduction to how we can display a molecule on a piece of paper, a 2-dimensional surface, such that it looks more 3-dimensional. So this is where we sort of bring our crude artistic abilities. And we have what we're going to call a dash and a wedge. The dashed line is going to indicate a bond that's going away from you into the paper, and a wedge is going to indicate a bond that is coming out of the paper at you. That's how we're going to indicate 3-dimensional orientation on a 2-dimensional surface. So for example, we could have ethane. When we have our 2 carbons that are going to be bonded to each other, we have a stick to indicate that those bonds are lying in the same plane as the paper. So that's right now just indicating that everything is flat in the paper like a little pancake. We have another hydrogen that would be behind the carbon going away from us. So that'll be our dash. And then we have another hydrogen that's going to be coming out of the paper at us. And we're going to indicate that with a little wedge. Sometimes we color these in. You don't have to. But sort of this is our dash wedge model. We don't have to make this molecule like this on the piece of paper, right? We could draw it like the line bond structure where we put the hydrogens in on purpose so that you can see what's going on. And we have what's called a sawhorse model. So we're pretending again that we're looking down a carbon-carbon double bond. So those are 2 carbons there on each of the points. To make it easier to see, we can put our hydrogens. Now again, if you have your model kit and you're building this molecule, this is where you would be staring down the carbon-carbon double bond, and all of the hydrogens would be eclipsing each other. So you wouldn't be able to see the hydrogens in the back because the hydrogens in the front are going to be in their way. That's just sort of how we're looking at this right now. Again, you can rotate around the carbon-carbon single bond, and you can change that orientation to spread out those hydrogens so that you can see them all, right? But this would be our sawhorse model. And then we have what, in my opinion, is just an easier method for sort of imagining that we're staring down the carbon-carbon single bond. So imagine that your eye is sort of looking down the bond, and you can see the carbon in the front, but you can't see the carbon in the back, right? So you're going to hold your model, your molecule up so that you're staring down in the direction of the carbon-carbon single bond. So you can't see the carbon behind, but you can see the one on the front. And the way that we're going to indicate that is we're going to put our carbon in the front with our little hydrogens, like this. So here are the hydrogens. So this is what you would be looking at, right, if you're staring at your molecule. And then what we're going to do is we're going to put a little circle around the carbon in the front. So here's your carbon in the front, right? If you have your model kit, you're staring at that. The other carbon that's behind it, you can't see. But we can put, oh, sorry, I kept the highlighter on. We can put our little hydrogens on like this. Let me erase that and put it over here. Keep it consistent. Try to keep these consistent, and if they're eclipsed in the other 2 models, we will eclipse them here. So you see the carbon in the front, you see the hydrogens in the front. We put the little circle, and then on the ring around the front carbon, we put the whatever groups are coming off of that carbon behind, in this case just hydrogens. We put those on the ring to indicate they're in the back. This is a Newman projection. There are different energies associated with where these groups, in this case they're just hydrogens, but where these groups are relative to each other in space. We are not stuck with this eclipsed conformation. With a carbon-carbon single bond, again, we can rotate around that single bond, and we can move these hydrogens to a more energetically favorable position. That is, instead of allowing them to be one behind the other in the eclipsed conformation, so I'll write that down here, this is eclipsed. If we rotated this 60 degrees so that all of these little hydrogens are staggered. So there's our front carbon with the 2 hydrogens. We put a little circle around this to indicate there's a carbon behind it. We're going to rotate around that carbon-carbon single bond 60 degrees. Again, all of the hydrogens that we have these little bonds coming off of the ring are indicating they're coming off the back carbon. In this conformation, and still a Newman projection, all we've done is rotate, right? So we rotate around the carbon-carbon single bond by 60 degrees. And now all of a sudden, all of these groups are staggered. This one right here is lower in energy. It puts all of those bonding domains as far away from each other as possible. It puts all of the hydrogens as far away from each other as possible. So, hydrogen's not like blocking out the sun or anything with its size. It's kind of small, but it does have a nucleus. And if we're bringing 2 of those nuclei near each other, there is a repulsive force associated with that. If you have the opportunity to rotate around the carbon-carbon single bond and spread out, give each of those groups maximum personal space, you will lower the energy of the species. So let me give you an example where we're not dealing with just hydrogens. So Newman, and I'm going to use the Newman projection instead of the dash wedge and the sawhorse. That's it. Like, I had to introduce that to you. Dash wedge is going to come in handy when we're doing stereochemistry on bigger molecules. So it was important to show you what the wedge means and what the dash means. But for these conformational isomers for the alkanes, we're going to be looking at the Newman projection because I think it's the clearest. It gives you the clearest picture of the front and the sort of behind. Now, if we were to make a molecule, like, for example, something that had more than just hydrogens, like if I have something like this. So in this case, I have 2,3 dimethyl butane. Remember, for our nomenclature, we have 4 carbons in the longest continuous chain, and we have 2 substituents, 2 methyl groups, one on carbon 2 and one on carbon 3. So we have 2,3-dimethylbutane. We're going to draw a Newman projection, and we're going to look down carbon 2 and 3. So Newman looking down. C2 and C3. So in other words, we are going to draw a Newman projection, and we're going to draw, if it helps, a little eyeball here. We're going to stare down carbon 2 and 3. It's an eyeball, by the way. So we're going to look down there. Let me get rid of that. So in one conformation, so we have our carbon in the front there. That's sort of like our little peace sign in the front there that we see. That carbon is carbon 2. On carbon 2, we are staring down the single bond between carbon 2 and 3. On carbon 2, we see that we have a methyl group. So I can put that, say, up here. The other bond that we have coming off of that carbon number 2, is going to be another methyl group, right? So that would be carbon 1. The other bond that we have on that carbon, other than the single bond between carbon 2 and 3, would be a hydrogen, which is simply just implied on the molecule, right? So we have a hydrogen here. On the back carbon, so carbon number 3, we have a similar situation. So if it helps to highlight, or I can circle these for a second, I've just drawn methyl group number 1, and I've drawn methyl group number 2. Doesn't really matter which is which, right? The hydrogen has been implied on the line bond structure, but I'm going to draw it in on the Newman projection. Carbon number 3 has a similar bonding situation. It's bonded to carbon number 2. It's also bonded to a hydrogen and 2 methyl groups. So in this case now, I'm going to say we've got a hydrogen and then we have these two, right? So in the back, I'm going to start out with the lowest energy conformation that I have, where I've staggered all of the bonds. I'm going to put the hydrogen here between these 2 methyl groups. There's another methyl group and another. So those are the 2 here that I've circled on the line bond structure. You can see that if I were to rotate around that carbon-carbon single bond, so I'm going to rotate 60 degrees to the right, just so you can tell what I'm about to do. I draw that same Newman projection, so I'm going to, basically, you're going to hold one of those carbons still and just rotate around that single bond. So I'm going to change what's going on in the back and just leave what's going on in the front the same. I mean, obviously, if I rotate 60 degrees in the front to the right and I rotate 60 degrees to the left in the back, I'm not going to see much, going on. But I'm going to hold the front steady. So I've got a methyl group. I'm going to make this a little bigger because those groups are going to be behind each other. So in the front, I had this going on. And I'm going to rotate 60 degrees to the right. So in other words, I'm going to go like this. $60. And what I've done, and the best way to do this, sort of like so you can still see the group in the back, because it's going to be directly behind the methyl group, is that I'm going to put this here, super close, so that you can still see it, but realize that's behind the methyl group. If I'm going 60 degrees over here, that puts this here. And if I go 60 degrees here, that puts this group right here, directly behind. So that's my best attempt at showing you that those 2 methyl groups are directly behind each other. This is going to be higher in energy. Because it's putting these 2 methyl groups one right behind the other. So those 2 methyl groups are eclipsed in that particular case. I mean, all these groups are eclipsed, but the methyl group is bigger than a hydrogen, so that's kind of a big deal. When you're looking for the minimum energy conformation, you're looking for something where you have a molecule that has these groups staggered, and you're hoping also that they're in the what we call anti-position. So if you're viewing this like a clock, you want one at noon and one at 6 o'clock. So the one in the front will be, say, at pointing up the top. The one down on the carbon in the back will be pointing directly down the bottom, and everything will be staggered. So the best or minimum energy conformation will be where you put these groups as far away from each other as possible. If you have these groups sort of like at a sort of 60-degree angle to each other, we have a word for that. Let me draw another example. Say we had just plain old butane. And we're going to look down that carbon-carbon single bond. In one instance, we're going to have the carbon in the front with a methyl group, and it'll have two hydrogens. I'm going to put a little ring around that carbon in the front. Behind it, we'll have carbon number 3 with the same situation. We're going to have a methyl group and two hydrogens. Notice how I put both methyl groups. So one of those methyl groups is bonded to carbon number 2, and the other methyl group is bonded to carbon number 3. And we're staring down the barrel of that carbon-carbon single bond between carbons 2 and 3. What I've done is I've put these methyl groups, not only all of these groups are staggered, right? But also anti. So they are 180 degrees apart. I have another option where I could rotate around the single bond. So we're going to hold the front steady. We're going to rotate around the single bond, and we're going to put our methyl groups 60 degrees apart instead of 180. In terms of energy, this will probably be the next best option. These are still staggered. And instead of anti, so they're not 180 degrees apart from each other now, they're 60. This is gauche. So this will be lowest energy. This will be our best conformation, or in other words, our minimum energy conformation. Or I could put these methyl groups one right behind the other, rotating again, and have them eclipsed. So I've got, imagine that's right behind the other methyl group. These hydrogens are right behind each other. So this right here is going to be eclipsed. And what we call syn. So 0 degrees. This is the worst possible scenario. This has the highest energy. And this is rotating around that carbon-carbon single bond puts that molecule at the highest potential energy, which is undesirable. So since this molecule has free rotation about that carbon-carbon single bond, and since everything is heading toward maximum free energy, right? Or we're going to minimize our potential energy. We're going to separate those groups as far away from each other as possible by staggering them and putting the groups anti to each other, so 180 degrees apart. This type of rotation is only available to us between a carbon-carbon single bond in an acyclic situation. If we have a ring, we're sort of stuck, right? Because we have carbons that are bonded together. So for cyclic compounds, we'll start out with a cyclohexane. We have our two-dimensional structure here. So here's our 2D version of cyclohexane. Our three-dimensional version of this molecule, we can write this a couple of different ways. One option, if you have a model kit and you want to make cyclohexane, pick it up and look at it from the side. There's two ways to view it. You can view it where you have the two end carbons. So say these two. If you're starting at the top, so by convention, again, we start usually at the top at noon, right? You don't have to, but when I say the end carbons, they're the ones that are across from each other, or the first carbon and the fourth carbon in this particular case. Pull those up toward each other. Make like a little hat. We call it a boat. Hard to write on this slippery surface, sorry. So we're bringing these methylenes up to the top like that, if you're building your little model kit. And I'm going to draw in the hydrogens. These are usually just implied, but just so you can get a sense, if you have your model kit, you can actually see these hydrogens move toward each other. There is an energy that exists between bringing those two nuclei close together, an undesirable energy. This right here is our boat conformation. And it'll be higher in energy than the other conformation I'm about to show you. So you have the option to put one of those carbons that I've highlighted up and the other one down. And if you do that with your model kit and you're viewing it from the side, you will actually see that it and you have to use your imagination a little bit unless you're holding it perfectly. It forms kind of like one of those lawn chairs that you can lay down in. So the easiest way to draw a chair is to take two parallel lines on sort of like an angle like that. And I'm going to connect these. I'm building my ring here, where I've got a long bond on the top going from left to right, or you could do it right to left. I'm just going to start this way in this direction. And then another line parallel to it from the other carbon down the bottom. That's long. And then I'm going to connect the carbons with shorter lines, also parallel. So it's not the most gorgeous chair I've ever drawn, but you get the idea. Those hydrogens, again, on carbon, say 1 and carbon 4, have been moved into new positions. Notice how, I'm going to highlight this in a different color so that you can see. Make this a little skinnier. Is that this bond right here and this bond right here are parallel to these. If you've drawn a more gorgeous chair than I, these will be parallel to these. Okay. So, and I'm going to highlight, say, these bonds. And again, I'm only doing the hydrogens for 2 of the carbons. Imagine that all of these carbons have hydrogens on them and they're doing the same thing. So we have a hydrogen here and a hydrogen here, and then one here and one here. Instead of having these sort of little flagpole hydrogens coming near each other, so I have, instead of these things bumping into each other or coming near each other, I now have these things sort of spaced farther apart. In this instance, any of the ones that are pointing straight up or pointing straight down, the position that we call that bond is the axial position. So like an antenna sticking up the top of your car. And this position and this position, any of them that are going off to the side, if they're going straight up and straight down, they're in the axial position. If they're going up and down, but they're sort of like off to the side, this is the equatorial position. This will be the position where we want to try to get our larger groups. Right now we just have hydrogens. If you have a molecule with, say, like 2 T-butyl groups in those positions, then it's a good idea, if possible, to have that ring flip itself in such a way that puts the larger groups in the equatorial position. It sort of pushes them out to the side and gives them the most space away from everybody else. And you can really look at this by making a model with your kit if you have it. So let me draw. So this is going to be our chair conformation. And I'm going to draw 2 of these and show you just the axial and just the equatorial positions on their own. So this will be our chair conformation. This will be lower energy, but depending on what you have bonded to this particular molecule, what groups you have on here, what goes in the axial and the equatorial position is going to affect the energy of the molecule. So for example, I could take a chair, and by the way, these are our 3D structures. So this is us trying to show that 6-membered ring on like a piece of paper or the blackboard or whatever on a 2-dimensional surface. We're trying to imagine like 3-dimensional occupation of space, right? So I'm going to take a chair. So again, 2 parallel lines, long bonds, shorter bonds. Imagine these are connected. Get a little lazy with my chairs. All of these positions, so up, up, down. Don't forget about these. Those carbons are easy to miss. So any straight up or straight down, these are axial positions. And if I draw a chair, same thing. All of these are our equatorial positions. Now, you see that, and it looks a little bit like they're pointing at each other, but go ahead and make the model with your kit, and you'll see just on the 2D surface, it looks like they're pointing at each other. They're actually splayed out like along the equator, which is why we call this the equatorial position. is a good time to mention that equatorial and axial do not necessarily stand for up and down, because notice how they're all different versions of up and down, right? I can have, in this particular molecule, I am axial at that position, but up. But this carbon, I have something axial that I've drawn in, and it's down. So again, we'll bring in our dashes and wedges to actually show the different types of isomerization. So like cis-trans isomers. If I've got two groups that are, hanging off of carbons in a ring, and they're both pointing up, sort of like towards the top of the ring, or they're both pointing down toward the bottom of the ring, doesn't matter if they're axial or equatorial. If they're both pointing in the same direction, up or down, they'll be cis. If I've got one group that's pointing up and the other group's pointing down, doesn't matter if it's axial or equatorial. They're pointing in different directions relative to the ring. They will be trans to each other, right? So here I've got one group that's going down, but it's equatorial. I've got another group here that's going up, but it's equatorial, right? So axial equatorial doesn't necessarily mean up down, but it does help us identify where these groups are hanging out in three-dimensional space, and it helps us to assess the energy. So let's get into, before we start talking about cis-trans isomers, different types of strain. These are the things that are going to affect the energy of your molecule. First type of strain, they call torsional strain. This is a situation where you're going to be bringing two atoms or groups, substituents, whatever you got going on, that are separated by 3 bonds. Too close to each other. This is a form of Coulombic repulsion. So we're bringing two groups or atoms that are separated by 3 bonds just a little too close together. And there is a force, a Coulombic force of repulsion as we bring those like charges just a little too close together. If it's easier to remember, think about the bonding domains. So the electrons involved in the bonding domains, we're going to bring those just a little too near each other. Another Coulombic type of repulsion, sometimes we refer to as steric strain. This will be like if I'm bringing two atoms or groups that are separated by 4 or more bonds a little too close together. And in that case, we're talking about either the 2 nuclei, if they're just hydrogens, or the 2 nuclei, associated with whatever's going on in the center of that other group, plus all their bonding domains. So there's like, if I've got groups or atoms that are separated by 4 or more bonds, and when bringing those a little too close together, we have what's called steric strain. So we're clogging up the works, basically. So we've got a situation where we're bringing two atoms or groups that are separated by 4 or more bonds too close together. Another form of Coulombic repulsion. And then If you're talking about a ring, there's another type of strain called an angle strain. Remember how these bonds are formed, right? We're going to force, if you're looking at like a ring structure, like up here I have like a cyclohexane ring, right? So I have a hexagon, right? In other words, if I'm going to be forcing the bond angles, so theta, right? If I'm going to force theta to deviate too far from what's considered to be the optimal tetrahedral configuration, in other words, I'm going to have theta deviate too far from the optimal 109.5 degrees, which is a perfect tetrahedron, right? I will be forcing what we call some angle strain. If you have a model kit, this will not be hard to imagine. If you go ahead and build these cyclic alkanes, so in this case, theta obviously is 60 degrees. In this case, it's 90 degrees. In this case, look how it changes a little bit as we get bigger. Doesn't mean the bigger the better, right? It's how close you can get to that 109.5 degrees. So this is just simply summing up all of the angles, right? So the sum of all of our interior angles is going to be equal to, remember from just like, I guess, fourth grade math, right? N minus 2 all times 180 degrees. So this would be like 108 degrees for these bond angles. And theoretically, this would be 120. The deal, though, with these is that for these molecules, so that's just for your regular polygon, right? But for 5-membered and 6-membered rings, we notice that there's a pucker. So the ring will pucker. And you can see this with your model kit if you build the structure. The ring will pucker to allow the angles to be closer to 109.5 degrees. So you will notice that in nature, cyclic compounds have a tendency to be found in the 5 and 6-membered ring category. 3 and 4-membered rings are difficult to make, and they're really easy to break open, right? Because that angle strain is greater. Imagine also if you're thinking about this from sort of like an orbital overlap perspective. In order to form a 3-membered ring, we have to force those lobes to overlap at not the best sort of, they don't get the best orbital overlap, right? Forming 60-degree angles like they would if they were forming 109.5 degree angles or something close to it. So we'll notice that when we're making ringed compounds, or if you're looking out in nature and you find natural products that have sort of like a cyclic structure, like you have a ring in your system, you'll see 5 and 6-membered rings more often than you'll see 3, 4, 7, 8. The medium-sized rings are kind of a pain to form, and the little teeny ones are really high energy and kind of a pain to form. But you'll see a ton of 5 and 6-membered rings. It just leads us to believe that that perfect tetrahedron is where it's at in terms of minimizing energy. We get back to different types of isomers. So these conformational isomers, a specific type, just specific to these ring structures, will be our cis-trans isomers. And we use them in the nomenclature to let someone know. where the groups are on the ring relative to each other. So chairs, and I'm going to use a chair instead of a boat because it's lower in energy, chairs can flip, right? They can flip to minimize their energy. If you have your model kit and you want to take whatever carbon you had up the top and make it the carbon on the bottom, and then the fourth carbon over that used to be on the bottom, you want to make it on the top. Notice how everything flips. So in other words, I could take something like this. You don't have to make like a beautifully intricate molecule. You could just put two methyl groups. One here, see that wedge? That's telling somebody that thing is pointing up, right? In this two-dimensional structure, that thing is up, and this wedge says this is back. So if I draw this three-dimensionally, so on a chair, make your chair first. Ooh. It's hard to draw on this slippery surface. Sorry for the squiggly chairs. All right, so I'm going to say this is carbon 1, and I'm going to let this be carbon 3. We'll just all agree to that right now, and I'm going to then say that this is carbon 1, and this is carbon 3. The way I've drawn this in the two-dimensional structure is I have a methyl group on carbon 1 that is pointing up, which means in this case I have a methyl group in the axial position pointing up. So let's number these so that we can follow these together. 1, 2, 3. Here I'm going to say this is 1, 2, 3. Right, so just so you can follow what's going on. On that third carbon, I have a dashed line going to the methyl group, which means it's pointing away, so down. There's two positions available at each carbon, axial and equatorial. If I'm going down, that puts that methyl in the equatorial position on that carbon. Notice how one methyl group is up on the top face of the ring, the other methyl group is down. These are trans to each other. I can flip the ring. When you flip the ring, whatever was axial becomes equatorial. Much easier to see if you actually make your model with your kit. So what that means is I'm going to put these, I'm flipping the chair now, so I've got my lines going in this direction. My long bond is now this one. My little short one goes up like that. Again, parallel to that, a long bond there. And then a short one. Sometimes it's nice to get a highlighter out just to remind yourself like what carbon you're talking about, because before I was dealing with on carbon 1, so I've highlighted there in yellow. That carbon is now this carbon. Carbon number 3 is now this carbon. So let me number these so that you can follow that. All I did was sort of push that carbon number 1 down. So there's carbon 1, here's carbon number 2, here's carbon number 3. Notice how carbon number 4 used to be down and now it's up. So that when you're building your kit and you want to flip these around, you just take carbon number 1 and carbon number 4 and flip them. That's it. Whatever was axial becomes equatorial. So now look at on carbon number 1, my methyl group, it's still up. That's important. It's because we have a wedge there, but it used to be up and axial. Now it's up and equatorial. The other carbon, carbon 3, has a methyl group, and on the two-dimensional structure, I have a dashed line, which tells me that it's going down underneath the ring. That on the first chair, put that in the equatorial position. It now puts it down, but it's in the axial position. See how you can be down or up, but you could be either axial or equatorial, depending on how you've put this on the chair. Now, in this situation, it's not that big of a deal because you have two methyl groups. If you had two big groups and they were cis, so larger groups, or even if they're trans and they're just larger. So for example, if instead of methyl groups, I put something bigger on the ring. So if I've got like a wedge here that says this is coming up at you, and I'm going to exaggerate this, but when I draw it on the actual ring on the chair, I'll do line bond structure. So you have a T-butyl group, and then in this position, we'll just stick another methyl group. The T-butyl group is obviously bigger, right? So again, I'm going to say 1, 2, 3. These are trans. You can tell just by looking at the two-dimensional structure. I got one group pointing above the ring and the other group is pointing below the ring. The dash and the wedge tells you that. However, if you were to draw out the three-dimensional structure and somebody wanted to know what the minimum energy conformation would be for this molecule, give yourself a chair. And you can start out by, we usually number that carbon 1, right? And then go clockwise around. You can do whatever you want as long as you're consistent with yourself. And I have a T-butyl group that's up, and that puts it in the axial position here. The third carbon over, I have a methyl group. There's a dash there, so it says that it's pointing down. So again, I'm just going to leave all of the C's and H's out of it and just keep it a line bond structure so it's clean. We're going to flip the chair. Whatever was axial will become equatorial. So in the first structure, I have a T-butyl group in the axial position on carbon 1, methyl group in the equatorial position on carbon 3. I followed what we call the stereochemistry. The stereochemistry is given that three-dimensional orientation in space by the dash and the wedge. So I followed that all the way through. I'm going to do that again on the next chair, but they'll still be up and down, as indicated by their dashes and wedges, but whatever was axial will become equatorial when I flip the chair. So flip your chair inside out. Whatever was axial will now become equatorial. So this is carbon 1. There's carbon 2 and carbon 3. On carbon 1, I have a T-butyl group and it's pointing above the ring as indicated on the two-dimensional structure with the wedge. So up, but now notice how it's equatorial instead of axial. On the third carbon, I have a methyl group that's pointing down, indicated by the little dashed line on the two-dimensional structure. It's still going down, but now instead of equatorial, it's axial. And if somebody were to ask you, what is the minimum energy conformation, it would be this one right here. It puts the largest group equatorial. You haven't changed the stereochemistry. It's still trans, right? It still puts the T-butyl group above the ring, so because there's a wedge there, but it puts it in the equatorial position instead of the axial position. If you had two T-butyl groups there and we had both of them sort of like, say you had something that was cis, so I can draw out a situation where they're both pointing in the same direction. So the top molecule we had trans. This is a situation where they're cis. They're both pointing in the same direction relative to the ring. You can see kind of why we draw these line bond structures. It gets a little messy. So this is cis. They're pointing in the same direction, right? We're both either above or below the ring. If I put this on a chair, and carbon 1, 2, and 3. I've got carbon 1, 2, and 3. On carbon number 1, I have a T-butyl group, and it's up. On carbon number 3, I have a T-butyl group, also up. Now, normally, if you want to really make this nice, you want to indicate that that carbon number 3 is in the front. So we can normally do something like this to show that that bond between carbon 6 and 1 is like behind that group. So we sort of leave a little gap there, and we let that group sort of shine in the front like that. But notice how these two groups are both axial. Now they look like they're not causing a lot of trouble there because I've drawn them just kind of neatly, but these take up some serious space and they're going to be banging into each other. We call this a 1,3 diaxial interaction. And it's bad news. So there's a strain associated with bringing these two groups too close together, right? There's a Coulombic force of repulsion. What the molecule can do, since you can't rotate freely around one carbon-carbon single bond in a ring, we can flip it so that whatever was axial will become equatorial. And you won't change the stereochemistry. You'll just change the three-dimensional space these groups occupy. So they'll still be up, right, relative to the ring, but there will no longer be that, well, at least you'll be minimizing the Coulombic force of repulsion as we give these larger groups more personal space. So again, here's carbon number 1, 2, and 3. Whatever was axial in the first ring, the first chair, is going to become equatorial. We're not changing the stereochemistry. So we have a T-butyl group. We often use T-butyl groups as like our, hey, check out this large group, right? Because it's a pretty big alkyl substituent. So you'll see these T-butyl groups used often to make points relative to sterics, right? If there's a steric hindrance, if I'm trying to attack a particular carbon and it has a big fat group on it like that, we say there's steric hindrance involved. Like there's the steric interaction. There's too much stuff in the way, bad energy, right? On carbon 3, again, the T-butyl group. Notice how they're both pointing up still. So we haven't changed the stereochemistry. They're still cis, but they're both equatorial. This is our minimum energy conformation. This puts both of your gigantic groups in the equatorial position. So that's going to be the better conformation or the minimum energy conformation. So that's going to pretty much do it for our conformational and cis-trans isomers. The last thing that we can really talk about with alkanes is going to be physical properties, and we don't need to spend a ton of time on this because they really only contain carbons and hydrogens. So dispersion forces, really. So your intermolecular forces are limited to dispersion forces. Right? So just carbon and hydrogen. The difference in electronegativity between carbon and hydrogen is really small. It's not zero because they're different atoms, but it's minimal. So I think if you were to put a number on, just using sort of like the Pauling scale, I guess you could say carbon is like 2.5 and hydrogen's probably like 2.1 or something like that, right? So there's a pretty small difference in electronegativity, so the polarity is not magnificent. So dispersion forces are really it. You're going to increase these again, just like we talked about in our review of Gen Chem. You can increase their significance with increasing mass, because when you increase the mass, you increase the number of polarizable electrons. So the effect that that will have for example, would be the boiling point. Will increase with increasing dispersion forces. Or mass, or structure. So I could have isomers. For example, I could have 2 or 3 different constitutional isomers that sort of, they all have different boiling points because the significance of the dispersion forces is going to be different as we make it easier or harder for the electrons in the species to be polarized. So you could take something like change in mass. So let's pull this down here as an example. We could have methane versus ethane versus, say, butane. And if we're looking at the, or I guess we could also include this one, get a big one in there. We're not changing the intermolecular forces of attraction. We're just making them more or less significant by adding mass, right? So I happen to have these boiling points jammed in my head. So we can use these molecules. Negative 164 degrees Celsius for just plain old methane. So at room temperature, expect methane to exist as a gas, right? Ethane, same thing, negative 88. But notice how there's a significant increase in the boiling point by just adding more electrons or more mass, right? So that we can increase the significance of the dispersion forces. Butane famously sits at 0 degrees Celsius, and decane is closer to 200. So you could change the mass or you could change the structure. So sorry to make this messy, but if we change up the structure, I could have, say, 2, 3, 4, 5. So N-pentane versus isopentane versus neopentane. And the boiling, so they all have the same exact molecular formula, C5H12, right? So all of them, C5H12, but notice how they're arranged a little bit differently. In the first example, N-pentane, they all have the same number of electrons, same mass, whatever, right? But those electrons are more easily polarized in that very first example, N-pentane, right? This is not all clustered up. We haven't clustered up the groups. Imagine that all those little bonds are like little electrical wires, or imagine they're like little ants that have to, the electrons are like little ants, right, that have to scurry on over. And, the fewer roads or the straighter the path, the easier it is. However you want to imagine it, right? The dispersion forces end up being more significant in that top example because it's less clustered. So we have constitutional isomers. They all have the same number of polarizable electrons. They all have the same mass, but they're just built differently, right? And we notice a difference in their boiling point as a result. So again, the boiling point is what it is. The story we tell ourselves is that we think it might have something to do with a difference in the significance of the dispersion forces, right? It's not the other way around. So we see the data and then we try to rationalize it. 36 degrees Celsius is the boiling point for N-pentane. Isopentane, 28. And neopentane is only 10. So there has to be something to that. And we rationalize that difference in that particular physical property by looking at the difference in the significance of the dispersion forces. So other than that, for these alkanes, these are not like the coolest molecules out there. What do we use these things for? So uses or reactions, right? They make good solvents if you're trying to dissolve something that's nonpolar. So good nonpolar. You want to clean up like a grease spill. Hexanes is great for that. So toluene or hexanes or benzene or whatever. If you got to dissolve something that's not polar but is organic, these alkanes or benzenes not obviously, and neither is toluene and alkane, but these hydrocarbons where all you have are dispersion forces, they make pretty good solvents. So like if you spill some oil in your lab, typically you'll see somebody sopping it up with hexanes, right? So good nonpolar solvents. And also we use them for fuels. So a reaction that we use, or a characteristic reaction, I should say, that alkanes undergo are combustion reactions. So for example, you could talk about like in your car. So gasoline contains a number of things, but one of the chief components is octane. So CH3, and we'll put the 6 methylenes in parentheses here. So there's octane. Combustion reactions, remember from Gen Chem, we're going to burn this in the presence of oxygen gas. Typically, we just indicate that with a little heat symbol under the arrow, right? And the combustion reaction of a simple hydrocarbon, we're going to get CO2 and water. So if we want to balance this, let's see, we have 8 carbons on one side and 1 on the other, but then that's going to make for an uneven number of oxygen. So if we multiply it by 2, this ends up being an 18, and that'd be 25 over 2. But if we multiply by 2, sorry, just rolling. Sorry to bring you into that. There's your balanced equation. This is a combustion reaction involving octane. So what you're going to get out of this is energy on the other side, heat. What is energy? The capacity to do work. So alkanes make excellent fuels. They undergo combustion reactions to give carbon dioxide, water, and heat. And that heat is thermal energy, and we can use that to do work, like propel your car, right? You can burn butane or propane. So butane in your lighter, propane, I guess, in your grill, whatever. Butane, I guess, if you're going camping, those little camping stoves. That's really it, when it comes to reactions with alkanes. There's some polymerization stuff. I'm going to leave that to the next grouping of compounds. We'll probably do some polymer stuff with alkenes. but this is really where the focus is for alkanes. They make good solvents for nonpolar molecules, and they make good fuels, and that's about it. Other than that, alkanes are pretty boring. So in the next group of videos, we're going to move into, in terms of your textbook, chapter 4, um, and that'll be alkenes and alkynes. And I'm going to smush chapters 4 and 5 together. So we're going to name and look at the structure of alkenes and alkynes in the next video. And then in the video after that, we'll talk about the reactions that we can do with unsaturated hydrocarbons.